everyone. Let us discuss concave and convex functions. Now, both concave and convex functions or curves are U-shaped. Both are U-shaped. Now, convex curve first decreases, attains minimum, and then increases. So this is the shape of the convex curve. So first it starts decreasing with the increase in x, with the increase in input or the influencing variable. So level of output y will start declining. Then it will attain minimum. Then with further increase, it will start increasing. So it, after attaining minimum, then it increases. Then inverse of this, inverse of convex curve is the concave curve. So in this, it is as inverse. So first, it increases at decreasing rate. So when x is going to increase gradually, y will increase, but at a decreasing rate. Okay. Then when it will reach b, it is maximum. That means corresponding to x2, it is maximum. Then if we increase x further, then it starts declining. So this is the shape of a quadratic production function. So in quadratic production functions, suppose y is equal to a plus bx minus cx square, then it will give this kind of shape of the quadratic function. So it is a concave curve. Now in both the curves, y is the function of x, okay? So y influencing variable is x and y is the dependent variable. So y is the function of x. Now in figure A, at point A for x1, at point A for x1, first derivative is positive. And then f prime x, that means first derivative with respect to x is positive, greater than 0. When we will feed the function with y data and x data, we will have this kind of form, quadratic form. Then if you take the first derivative, then it is positive. But while second derivative is negative. The nature of the curve is such that it is increasing. That's why first derivative is positive. But at what rate it is increasing? It is increasing at a decreasing rate. That's why second derivative is negative. Now at point B for x2, so first derivative is 0. Here it increases and increases. That means it is declining, increasing at declining rate. Ultimately at B, there is no increase. It is the maximum. After that, there is no increase. So at B, first derivative is 0 and second derivative is negative. At point C for x3, again first derivative is negative. It is declining. Because it is declining throughout. Here it was increased at decreasing rate, but here it is declining. So that's why first derivative is negative here. Earlier it was positive at point x1. So it is negative. Then second derivative is negative. In figure B, first derivative at x4 is negative at point D, and second derivative is positive. Second derivative is positive. Then at E, first derivative is 0, but it has attained minimum, so there is no further change. So first derivative is 0 and second derivative is positive at E. At point F, first derivative is positive and second derivative is also positive. So it is increasing. So both are increasing, that's why both are positive. Now in figure A, g prime x is negative, and as x increases, slope of the curve decreases. It is reversed in figure B. In concave curve, if we join any 2 points, suppose in concave curve, suppose there are points M or N, M here or N here, if we join these 2 points, M and points, suppose, so it will be below the line segment, lying entirely below the curve. So the curve, if we join, it will be it will lie below the line, below the curve. It will not outside. It is otherwise for convex curve. So it is just reverse in convex curve. So they are strictly concave and convex curves. So in that case, it is said that these curves are strictly concave and strictly convex. At all points, if second derivative is negative, the curve is strictly concave. So we have seen earlier that all second derivatives are negative. This means the curve is strictly concave. When it is positive, it is strictly convex. So these are the two sufficient criteria, that if second derivative is negative, it is concave. If second derivative is positive, it is convex. And they say that there may be some exceptions. For example, in this function 4x, suppose fx is y is the 4x square. Now f prime x, that means x to the power 4. It is x to the power 4 origin function. First derivative is 4x cubed, and second derivative will be 12x square. So it is indeterminate whether it is positive or negative. That's why there may be some exceptions in this criteria. So in case of downward sloping indifference curve, so we know indifference curves. So utility is the function of two commodities, x and y, or q1 and q2, and indifference curves are downward sloping, we know it. So in case of downward sloping indifference curve, bordered Hessian determinant, so it is bordered Hessian determinant, H determinant H means it is a bordered Hessian determinant, is positive and strictly convex. If border Hessian determinant is positive, it is strictly convex. The function is strictly convex. Now in case of multivariate case, suppose z is a function of a set of x, x variables, not one x or two, but more than one variables. Suppose z is the function of x1, x2, so on up to xn, n number of variables are there. So in that case, what to do? What are the criteria? Then conditions are different in this case. So for maximization of this kind of functions, so first derivative, all first derivatives should be equal to 0. So derivative with respect to x1, suppose the function is defined, then first derivative with respect to x1, then second derivative with respect to x2. That means the first derivative with respect to x2, first derivative with respect to x3, and so on up to xn, put all them to equal to 0. It is the first order condition. Then find out the Hessian determinant. We have already discussed in earlier chapter that the Hessian determinant. What is a Hessian determinant? We'll discuss later on also. So Hessian determinant should alternate in sign. That means if the first determinant is negative, second should be positive, third should be negative, and so on. It should alternate in sign. If it alternates in sign, then we say the function is a maximum function. It can be maximized. Now, maximize means, as we have discussed just now, that it is a concave curve where the maximum point is there, and minimum. So same criteria, first derivative of all variables should be put to 0, and Hessian determinant hi, I have written hi, that means h1 should be positive. It is positive throughout. That means h1, first Hessian determinant is 0, is positive, second is positive, third is positive, like that. There is no question of alternating sign. It is throughout positive. So in that case, it is minimum. That means the curve is declining, attains minimum, then it has increased. So it is a case of your convex. If the function is strictly concave or convex, d square z, that means it is the second order total differential. So we must have the knowledge of difference and differential. So d square z will be negative or positive at any point on the function. So it is same with minimum or maximum criteria. So d square z will be negative or positive definite, and the Hessian determinant, it is Hessian determinant is positive definite if q is invariably positive, that means greater than 0. If negative, that means less than 0, it is negative definite. Now we will discuss what is q. So this is the second order total differential. D square z is equal to fxax dx square plus 2 fxy dx dy plus fyy dy square. and quadratic form Q is equal to AU square plus 2HUV plus BV square. Now, what is this? So this is Q is equal to dz. Here U is equal to dx. P not it is equal but identical. P identical to dy. A identical fx. For fxx we have substituted A, and for fyy it is B, and h fxy and or fyx. Okay, so this second order differential, then it can be written in this form. Okay, in this form. So if it is less than 0, it is negative definite. If it is greater than 0, it is positive definite. Now, Hessian determinant is like this. We have already discussed earlier also that f11, f12, suppose there are n number of x, n number of variables, independent variables, then f1 means first derivative with respect to x, then again derive the first derivative, this is f11. Then first derivative, then derive with respect to, next you derive with respect to y. So this is with respect to same, first and second, same, but here first derivative with respect to first variable x, then what result we get, then you derive with respect to y. That means next variable, like this. So f21, f22, so on. So determinant of this, that is the bordered Hessian determinant. Now H1, determinant H1, H2, so on up to Hn are principal minors. Principal minors. So H1 means you delete this row, this column, then determinant of this, that is H1. Similarly. So coming to quasi-concave and convex functions. So this is a critical point. Quasi-concave and quasi-convex functions. There are many examples of use of quasi-concave and convex functions in economics. Now, what is the meaning of quasi in dictionary meaning? Meaning is that it says the quasi means not really. It is seemingly or almost. It is almost same, not exactly same, but almost same. It is not really the same thing, but it is nearness to that, like this. So quasi means not really, seemingly, or almost. Now, there is a good example of a bell diagram. So we know the bell diagram. The bell is used in the temples and all, bells. Sorry. So the bell diagram indicates a strictly quasi-concave functions. Now significance. The segment UV give rise to the arc Mn. This is UV and Mn on the surface. If M is lower than or equal to n. So we have seen that m is lower, n is higher, and m is at lower level. So it is said that any point in between m and n, will be on the arc mn other than m and n. So must be, that point must be higher than m. Must be higher than m. So any point in between m and n must be higher than m. Let us exemplify the diagram. Okay, this will be better. So now what is algebraic interpretation of quasi-concave and convex functions? Now function u smaller than or equal to function v. Function v. Because you see we have here the u is at lower level, v is at higher level. So function u less than or equal to v. So implies or equivalently, if we multiply u by a scalar lambda, that means lambda may be any values, any value, suppose 10% or 15%, that means 0.1 or 0.5, 0.10 or 0.15. So rest will be 1 minus 0.1 or 1 minus 0.15, because the value of lambda assumed to be to range between 0 and 1. 0 and 1. So if lambda we have assumed say 20%, that is 0.2. So this will be 1 minus 0.2, that means 0.8. So the function after multiplication by the scalar lambda u plus 1 minus lambda v should be greater than the function u, or equivalently function uv plus 1 minus lambda v greater than minimum of function u or function p. So this will be some set of values. Function u and function v means it is set of values. So in the figure there are two situations. So let us see this exemplified. Now in the figure there are two situations. Arc mn, where m is less than n. So this is mn, m is at lower level and n is at higher level, less than n. And another arc m prime n prime, where m prime is equal to n prime. Now in this case the arc, this is curve, passes through m prime and n prime. So this arc is considered as part of the indifference curve above u prime v prime. The above algebraic definition so also satisfied by the strictly concave function. Thus a quasi-concave utility function may contain both concave and convex functions. So it is said that from this illustration, it is said that in the indifference curve, a quasi-concave utility function may contain both concave and convex functions. But it may not maintain the increasing or decreasing marginal utility. So when there is concave and convex both, so the quality or significance of marginal utility curve, marginal utility function, say increasing or decreasing marginal utility, so there may not exist. Now, algebraic definition of strictly quasi-convex function. So function u less than or equal to function v implies if we multiply by lambda u plus 1 minus lambda v should be less than the function v. Earlier it was function u. In case of concave, now it is less than. Earlier it was greater than u. Now it is less than function v. So value of lambda ranges between 0 and 1. Or equivalently, lambda u plus 1 minus lambda v, so less than maximum of function u and function v. So earlier it was minimum of function u and function v, set of values of u. But in case of convex, quasi-convex, it should be maximum of function u and function v. So geometrically, it is like an inverted bell. So we have shown the bell, strictly bell shaped, but if we invert it, it looks like this. So geometrically it is like an inverted bell. Arc m prime n prime satisfies the first function but does not satisfy the function of strict quasi-concave. So it does not satisfy the strict quasi-concave. Say exact opposition is true in the next diagram. So in the next diagram, it is observed that there will be change of sign, greater than sign, to weak inequality sign. So in this case, instead of using greater than sign, we will have to use the weak inequality sign, greater than or equal. It should be observed that if a function is quasi-concave, then the function minus f must be quasi-convex and vice versa. That means if the function is quasi-concave, the negative of that function is the quasi-convex and vice versa. So this is all about convex and concave functions, and some ideas about quasi-convex and quasi-concave functions. So with this, I thank you everybody for watching, and keep on watching and share. Thank you very much.